The Materials and Electrical Components Laboratory supports all ESA projects to ensure the success of the mission and also to guarantee an optimal choice of materials and processes for the ESA missions and also the external projects.
One of the big areas that all spacecraft designers are interested in is something called end-of-life performance. And that means that basically after so many years, of course, your spacecraft is still working. And time temperature superposition is a technique that we use to try and establish predictions of how the condition of a material at its end of life.
Of course, the best way would be for us to test the materials over 15 years and to verify that they function properly. However, this is not the most economical way for us. So that's why we need to perform some accelerated testing in order to decide on a shorter time scale if they can fulfill and they can keep actually their critical functions in an extended period of time.
Thermal analysis is a way of looking at the material's response to a range of temperatures. And often we have to use more than one technique to understand this. DMA is dynamic mechanical analysis, and it looks at how a material responds to a dynamic environment, i.e. we apply a load and look at the mechanical response of that material. And from that, we estimate the viscoelastic component of something called the modulus, which is really just stiffness. Because I'm sure you've all encountered this, a rubber at low temperature gets much more brittle. At 100 degrees C, it's probably a little bit more flexible. And what the DMA really does is measures those effects. And then we use that in a technical interpretation, in this particular case for something called time temperature superposition, which is where we can move these effects on the time axis because we've modified the temperature axis, and we can look at acceleration effects and start making some predictions on how a material will respond in a longer duration compared to what our experiment is. One of the other instruments is thermomechanical analysis, TMA. And put simply, it's really just a very accurate ruler. It's a way of measuring a sample and looking at how it expands or contracts with temperature. And in a space environment where we can be anything from minus 175 degrees C in the extreme, all the way up to, if we took examples from Bepi Colombo, which is 300, 500 degrees C for solar orbiter, we obviously know that material is going to expand and contract across that range. Now, on its own, that's quite important, but if you couple those materials by bonding them to different materials, say, you end up with two different expansion rates. So you imagine where we've, say, stuck a piece of metal to another piece of metal which is different, we would end up introducing some stresses. And those could cause a failure, could cause a problem. We need to design for that and understand, is it a problem before we launch? It's really important because we do not get to go and repair a spacecraft. It's not like your car, if a piece breaks on it, we can take it back to the garage and okay, we have to pay, but it's repaired. Now, of course, when someone's paid hundreds of millions of euros to have that mission in space, it's not very good if we say, well, we didn't do our job very well and we misinterpreted where a material would melt or where a material would begin performing less well. So we have to be confident before we launch the spacecraft, and this is why it's really key to understand these fundamentals. One thing I can say about people who work for the European Space Agency, myself included, is that we do all have a great passion for the job. We do find what we do interesting, challenging, quite often frustrating, but ultimately rewarding. And I think to a large part that's why we're here, and I certainly feel part of that group.